Okay, let's begin. Okay, 8, how do you do that? Yeah? Yes?
Chain rule.
Chain rule?
So sin x derivative of sin x is cosine x, and then find the derivative inside is 2x.
Okay, so that's the important part here. I want you to realize when someone writes this, they mean that. And so this would be differentiate the outer function, leave the inside alone, then multiply by the inner function. What about the second one? Yeah?
Can you use the product rule because it's cosine x and cosine x?
So, right, this one is actually cosine times cosine. So you could use the product rule. You could also realize that this is actually just cosine squared. So I'd probably pick this one. Not that this would be wrong. I think this would just be slightly longer to figure out. But you could actually think of it as this and do the product rule, or think of it as this and do the chain rule. So, but the important part is to realize when the square is on the cosine, it's the entire thing squared. But if the square is just either in the angle or hanging off, it's a completely different scenario. Okay, so this one we can think of as the derivative of cosine x all squared, and then applying the chain rule in this case, the 2 comes down, leave the inside function alone, subtract 1 from the power, multiply by the derivative of the inside, which in this case would be minus sine of x. And that would give us minus 2 cosine x sine x. What is 2 cosine x sine x? Can you simplify that? Rewrite it? It's the double on the formula for sine. So that's sine of 2x, where 2x is in parentheses. Okay. What about the third example? Give you the absolute value of x function. I would like you to find the derivative at the point 0. How would you do that? Yeah?
The answer does not exist.
Why?
Because at the absolute value, let's take a sharp point, which is x would be 0, and find the slope, you can't divide by 0.
Okay, so there are a couple ways you can see this. One, so it's essentially what you said, but let's actually realize why that is. We could do this by definition of the derivative. So we do realize that f prime of 0 would simply be the limit as h approaches 0. So I do it this way because you mentioned division by 0, so I want us to realize where that would come from. So that would be, by definition, what the derivative evaluated at 0 would be. And what is this? F of 0 plus h, if my f of x is absolute value. Right, absolute value of 0 plus h. Right, which is absolute value of h. What is f of 0? Absolute value of 0 all over h. Now, of course, this would simplify. Absolute value of 0 is 0. 0 plus h is just h. So this simplifies to this guy. Now, that is actually a limit we looked at before, a couple lectures ago. And you would realize that this does not exist. Right? Because this guy has 2 things going on. I mean, it's the limit as h approaches 0. If you're coming from the left, this gives you minus h, and so that will give you -1 as the limit, whereas if you're coming from the right, the absolute value will give you just h, that will give you positive 1 as the limit, and those two sides did not agree. And you could have done this from the beginning, where you realize that the derivative, so another way you could think about it is that the derivative of the absolute value is, especially if you're worried about 0, you'd have to, it branches off at 2 points. It's this guy if your x is greater than or equal to 0, but it will give you this guy if your x is less than 0. Obviously at 0, these guys would not agree, right? So it'll be 1 in one situation and minus 1 in the other situation, where at 0, these two do not link up. It's not a meaningful answer. And so yes, it can look like from the graph, and it turns out here, you know the derivative is not going to exist because it's a sharp corner at 0. Now, you might ask the question, why is a sharp corner a problem? So here we have a sharp corner at x equals 0. And this is a problem. Because, remember how we developed the derivative? We basically took the idea that we're going to approximate a function with a straight line and use the slope of that line to determine the slope of the function. And it just so turns out, if you zoom in on a sharp corner, it will never look like a line. It's never going to flatten out. It's a sharp corner, right? So when something is like curved, you can say, well, if you zoom in far enough, that'll start looking like a line. Thing is, with a sharp corner, it's never going to be true. Okay? You can't approximate a sharp corner with a line. It doesn't flatten out as you zoom in. So our flat earther approach just won't work here. So this leads us to some remarks that I want you to be aware of that apply because of the idea, how we actually constructed this thing called a derivative. These ideas would apply right away. F is differentiable at a point, meaning we can find its derivative at some point if it is approximately linear at that point. And what I mean by approximately linear is when you zoom in, it looks like a straight line. It kind of flattens out if you take the right scale, right? That allows us to approximate it with a straight line, which we call a tangent line, and the slope of this tangent line gives you the derivative. Okay? So, i.e., the function looks linear when zooming in. This can't work with a sharp corner. And this example leads to this idea, the existence of the derivative. So we remember a derivative is a limit. It is possible for the limit to not exist. I just showed you an example of why. But there's also some intuitive understanding of when this limit would not exist. Sometimes you don't even have to find the limit. You can actually look at a function and tell that you can or cannot find the derivative at a certain point. So the existence of the derivative. Right, so the derivative was the solution to the rate problem, was a very big deal, but it is not all powerful. You cannot always apply it. So this is one case in which you cannot apply the derivative, which was emphasized by this one. The derivative limit may not exist. You cannot take a derivative at. Here are the scenarios in which a derivative will not exist, and you should know these scenarios. One, a point where there's a sharp corner. Fancy word for sharp corners, the cusp. So the derivative does not exist at cusps. So if you have a function that's doing something like this, or behaving like absolute value of x, it turns out that there are tons of tangent lines I can draw through that point, and all of them will equally be valid. Right? It's no way to define a specific tangent line. Who would be the tangent lines? Undefined. You can draw a bunch of lines to that point, and none of them is pretty much going to approximate that point, because no matter how much you zoom in, the sharp corner will not behave like any of those lines. So it turns out the derivative will not exist at sharp corners. So even if you don't know what the function is, or you can't find the limit, or you don't know how to differentiate it, if you can get a graph and you look at the picture and there's a sharp corner, you know the derivative will not exist there. Another scenario in which a derivative will not exist. It will not exist at a point of discontinuity. Turns out that the function needs to actually be there in order for us to draw a tangent line there. So if you are a hole or a gap, etc. Again, these guys would never look like a straight line no matter how much you zoom in. You can't actually plot a tangent line through a point. This is one of the reasons why continuity was so important, why we took some time to talk about a function being continuous. Turns out where a function is not continuous, our derivative is not going to work there. It will be invalid. So we cannot solve the rate problem at points of discontinuity. So a lot of times you'll have to try to figure out if the function you look at is continuous before you even think of trying to do calculus there. Because if it's not continuous, it's not going to work. You will need to examine the function some other way. There's a third scenario in which the derivative will not exist. It will not exist at, I already put the at there, a point where there's a vertical tangent line. Now you guys know how function works. You know that functions are things that pass the vertical line test. So how could you have a vertical tangent line? A function is never supposed to be vertical at any point. It turns out that there are very weird examples of functions that they approach a vertical line, but they do that literally for a single point. So it allows them to pass the vertical line test without actually being vertical for more than one point. So you would have a function that has a weird behavior like, okay, it hits this point, and then it immediately changes its behavior like this. This kind of behavior we'll talk about, by the way. But it turns out if you zoom in, the best approximation to that behavior will actually be a vertical line passing through the point. Prox at this point. Right? So it does that for a single point, and it just turns out if you happen to zoom in closer and closer to that point, it seems to look closer and closer to a vertical line. However, vertical lines have no slopes. But a derivative is just another name for slope. It's a synonym, in fact. So this means they have no derivative. Because the derivative is the slope of the tangent line, which is the best linear approximation to a function. And in the case that the best linear approximation is a vertical line, there is no slope to speak of. So it turns out functions that will behave like that, you actually won't be able to actually find a derivative at that specific point. So we spoke about the derivative and all sorts of rules and properties. One thing you should also know is when your derivative won't work out. Okay, so these are the three scenarios, right? Either you'd have a sharp corner, point of discontinuity, or a vertical tangent line. And these guys will make your derivative limit invalid. The limit won't exist or something like that. Or the limit won't exist. That's what's going to happen. Or in that case, the limit will give you like infinity or something, which is not really a slope. You can't say something is moving infinitely fast. It's not really a thing. So that's just something you have to know about. But the next important topic I want to talk about is going to be implicit differentiation. So these are just things to be aware of. Okay, so there are three situations in which you can't find a derivative. Sharp corners, points of discontinuity, and points where there are vertical tangent lines. So, pretty much if a function behaves not like one of these ways, we can always find a derivative there, in theory at least. But there might be another problem when it comes to finding derivatives, depending on how our function is defined. And this leads us to another topic called implicit differentiation. And this is used to find the derivative of implicitly defined functions, which are far more common than you would think. Perhaps just as common as explicitly defined functions. So let's start there. First, let's talk about what is an implicitly defined function. Functions there are two main ways we can define a function. We can break functions into two groups. One is called the explicit way, or explicitly defining a function. And this is pretty much when well, it's pretty much what we've always been doing up to this point. Right? So like y equals x squared, or y equals x plus 1 over x plus 2, or y equals ln x. Basically, it's when you can say y equals f of x. Right? Your y is explicitly out in the open, and you can fully define what your dependent variable is doing wholly in terms of the independent variable. Right? So tell me what the x's are doing, and I can use that information to figure out what the y value is doing. And the y value is explicitly defined in terms of some generic formula for the x value. So that's when your function looks like this, which is what we've been looking at this whole time. But there's another way to define a function. It's called the implicit definition of a function. So the function definition can be implied, but it's not explicit in terms of the independent variables, because you could have something like the x's and y's are mixed together. It's like xy equals 1, or x squared y squared plus 2x equals log of y, or any such number of things. Your x's and y's are kind of mixed together. You don't have y equals and something with only x's to worry about. Right? So it's kind of like you have this is a multivariable function. It's some rule that deals with some amalgamation of x and y equals some constant. So this is the explicit way to define a function, which we've been looking at this whole time, and probably for most of your life. And there's an implicit way, like a circle also, by the way. So we know circles aren't functions, but you can think of a circle as defining a function implicitly. Right? There are implied functions here. In fact, this equation implies two functions, right? There's the y equals the positive radical of 4 minus x squared, and y equals the negative radical of 4 minus x squared. So you can, a definition can be implied in some sense. Now, we know how to differentiate this, right? We know how to differentiate here. Right? It's what we've been doing. Constant factor rule, product rule, quotient rule, chain rule, all that stuff. We know how to deal with these. Told you the rules for the basic functions we'll be doing. So we do know how to find derivatives implicitly. We even did some examples last time. Here though, how would you actually do that here? It turns out, the trick here, if you can call it a trick, it's not really a trick, is to apply the chain rule. So the chain rule is very important for a multitude of reasons, but another reason is that it helps us define y prime, or dy dx, in a situation like this. So let me illustrate how this would work, and then we'll do some examples. Let's just leave things kind of in terms of x for now. Suppose I wanted to find the derivative of some function of x. What could I say that's equal to? Versus, let's find the derivative of some function of x times a function of x. What would that be equal to? Let's say I wanted to find the derivative of x divided by some function of x. What would that look like? Maybe also finding the derivative of, say, the log of some function of x. What would that look like? Versus something that looks like this. So it's x squared times some function of x. So Now this one's kind of where you probably don't know what I'm asking for here, so let me just give you an example, and then you should be able to finish off the other ones. I can rewrite this in just a different notation. Just say the derivative with respect to x of f of x is going to be the function f prime of x, whatever that might be. Okay, so we're not specifying what this function is, but I know its derivative is going to be whatever the derivative limit is, f prime. Okay, what would this guy look like if I wanted to differentiate something that looks like this? Yeah?
X, f prime of x plus f of x. Plus f
Or
of x.
1 times f of x, just to emphasize that you're actually using the product rule here. Okay, so you leave one function, differentiate the second, plus differentiate the first, leave the second. Okay, not too bad here. What about this one? What would this be here? X divided by some function. Yeah?
Quotient rule.
Use the
So
quotient rule.
it will be 1 times f of x
Alright, the bottom times the derivative of the top.
minus x times f prime of x divided by f of x whole square.
Now these you'd really start. Now we've been using the chain rule the whole time. You might not have noticed, but you should be noticing here. Oh, this one would go. Yeah?
F prime of x over f of x.
Right. So remember that the derivative of ln x is 1 over x. So you'll start by taking 1 over f of x, and then you multiply by f prime. So you get f prime over f. Okay. Now that's a pretty, I don't want to say explicit use of the chain rule, because this is kind of implicit case, right? You don't actually know what this function is. There is a definition suggested or implied. It is some function of x, we just don't know what it is. But I can still find, as a formula or an idea, its derivative. It'll just be 1 over the function times its derivative. What about this one? What definition of this, the derivative of this be? Yeah?
You can rewrite it based on like take the whole power of the function, because so it will be x times f of x like whole square,
Okay.
and
what would-
then do the chain rule.
Okay. And what would that look like? X times f of x all squared. And do the chain rule. So to apply the chain rule here, you'd have to apply what on the inside here?
The product.
You need to apply the product rule. I would just apply the product rule as is. Let's do it like that. Let's just do the product rule, because we're going to have to do it anyway. So what would that look like here?
Do
Well,
x
Differentiate the first function, leave the second one alone.
plus x squared times 2f of x times f prime of x.
Right, you have to apply the chain rule here, right? So again, in all these cases, our f of x is some implicitly defined function. I don't even know what the definition is, but the idea is whenever I want to differentiate that part, I have to multiply by an f prime, right? Because the chain rule says that's how I have to do it. We can think of this f of x as some kind of inside function that's plugged in there. And so whenever we are taking a derivative of an expression that has such a function, we have to remember to keep multiplying by f prime in every situation. So you realize that an f prime shows up in all these cases whenever we're dealing with the derivative of the f of x part. So now that is going to make what I write now make more sense, hopefully. Because somehow when you change the notation, it confuses a lot of people, but I want you to realize it's a very normal way of doing things. In the same way, if I were to ask you what is the derivative of the function y, you would tell me, oh, it's y prime. Versus, if I asked you, what is the derivative of x times y? Well, you'd say that's the product rule. It's going to be derivative of this times y plus you leave this and you differentiate the y. We did it in the other order, but you can see it's the same thing. I could ask you, what is the derivative of x divided by y? And you would just do the quotient rule. The bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. The fact that there's a y there shouldn't scare you. You just know you can deal with it by finding the chain rule. Similarly, if I were to ask you, what is the derivative of ln of y? Well, that would just be 1 over y times y prime. If we had to differentiate something that looked like x squared y squared, right? And again, your y here is just representing some function that you might not know what it is. You may or may not be able to define this definition, but regardless, you can differentiate an expression like this by the product rule. Differentiate the x part, leave the y part alone, plus leave the x part alone, and differentiate the y part. So now, how do you differentiate y squared? Well, the chain rule. Think of the y as some inside function. Bring the 2 down, leave the inside function alone, and then multiply by y prime.
I have a question.
Yes?
So do we take common factor in the last one? Because we can take 2x f of x.
You could, but I'm not concerned about simplifying at the moment. Right? We'll see that later.
But we do that right.
Huh?
But we do when we're solving that right.
Sure. It depends on the situation. I just want you to understand how you find the derivative of such an expression. So when your x's and y's are mixed up, pretty much you differentiate as you would normally. The product rule still applies, quotient rule still applies, all the rules still apply, chain rule still applies. But in particular, applying the chain rule to something like this, if I'm differentiating with respect to x, and there are variables other than x, every time I differentiate such a variable, I must multiply by its derivative, because I need to apply the chain rule. Okay? That's the part I want you to get. Okay. Now, hopefully with that understood, we can start to look at some examples here. And one reason why this is important is because sometimes, a lot of times, we'll talk about some applications next time. We mentioned some specific ones from chemistry. But sometimes when you're trying to model a phenomena, the rule or the function that describes it does not come to you in an explicit sense. It comes to you kind of where the two quantities you're looking at are kind of attached in some way, and you can't really separate them. But you'd still want to be able to talk about rate of change and the speed at which something is changing in these scenarios as well. So if you end up in such a case, how you would go about finding derivatives and solving the rate problem would be implicit differentiation. So we'll look at 3 examples now, but we'll have more in the next class. So the goal here is to find dy dx. In other words, I want to find y prime in these scenarios. So suppose x times y equals 1. Find y prime. Find a formula that describes the slope on that curve. I could also have something so this one. So those 3 examples. You're examining some system, tracking 2 quantities, and it turns out that these were the relationships that the 2 quantities share. And now you want to figure out how fast is the y quantity changing with relation to the x quantity. That is our goal. We want to figure out that. So for x times y equals 1, how would you do that one? How would you find y prime? Right, so this is given to you. Boom. X times y equals 1. Find the derivative. Find y prime. Yeah? What would you do?
Maybe y plus x, y prime equals 0. My derivative of both sides.
Okay, so you can differentiate both sides of the equation. Right, so what we're going to do here is differentiate both sides. Right? So now the thing is, how would you differentiate that? Well, the product rule, it's a product of things, right? So you don't forget the old derivative rules, they still apply. So I'm going to differentiate one thing, leave the other thing alone. Plus, leave the first thing, differentiate the second one. The derivative of this is 1, but you have to multiply by a y prime because of the chain rule. Equals derivative of 1, 0. Derivative of constant is 0. Now the question is to find y prime. Now you're in a situation where y prime is just one member of an equation that you need to solve for. Now it's just a matter of algebra and finding y prime. So what you can do is just move this guy over that side. And then you just solve for y prime by dividing by x. And so you'll be able to say y prime is equal to this. Yes, it might be a little weird to you that there's a y over on the right side, but really solving for something in an equation just requires that the thing that you want to solve for is not on the right side. So there's no y prime on the right side. So even though it's kind of weird that there's a y on the right side, this is not illegal or undesirable in any way, really. I do want to emphasize that there was another option here. So given x, y equals 1, I could have just solved for the y in the first place. I could just solve for y by dividing by x. Which I know is not, well, we should have worried about it here, but let's just deal with it here. I know I can do this because our x is not equal to 0. How do I know that x is not 0? Yeah.
Because we're multiplying it with something
Right, because when I multiply with something, I get 1, right? So if your x was 0, you would get 0 over here. You wouldn't get 1. So I know x is not 0, which means I'm allowed to divide by it. By the way, that's the same reason why I could divide by here. I know x cannot be 0 here. So I could rewrite this, solve for y, and now that's just the power rule. So now I can realize that this is just x to the minus 1, which means that my y prime is just going to be minus x to the minus 2, or minus 1 over x squared. That's my y prime. Okay, so you probably have some concerns. Let's do some questions. Do these answers agree? Because they should, right? Trying to trick me, Javon? You told me the answer was minus y over x. Now you're telling me the answer is minus y 1 over x squared. Which is it? Or is it either? Or is one of them wrong? Maybe I was wrong about the whole implicit differentiation. Yeah.
If we just solve for x, like we plug in 1 over x for y in the first one, it should be the same answer.
Right. We know, or we can know easily, that our y can be written as 1 over x. This means if I look at the expression minus y divided by x, this guy over here, well, that's the same as minus 1 over x over x. Well, that's the same as minus 1 over x squared. So yeah, they do both work. This is as valid of an answer as this one is. In fact, we can clearly see here, without too much trouble, that the answers agree with each other, they overlap, they are essentially the same answer. right? They might be written in a different way. So what this guy shows us is that implicit differentiation is optional. Sometimes. So this one was a particularly nice example, but things can get a little bit weirder. Let's look at the second example. So here was an example where, yeah, it's kind of overkill applying implicit differentiation. Just solve for the y, and it'll be easier. Okay, well, let's see what the second example is. So let's say you're not into implicit differentiation. So you decide, you know what, last problem we could solve for y, let's try solving for y in this problem and find the answer. Could we solve for y here? Well, we can. Does anyone see how? Yeah? What's your idea? No? Yeah?
You could take y as the common factor in first two terms,
Okay.
and then do something with it. I don't know. Yeah.
Does this help? Now, do you see how to solve for y?
Oh, that's the quadratic.
It's a quadratic. It's a quadratic in y. We can solve for y. It's a quadratic. So I could actually solve for y here. Minus b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. That is my y. I could actually solve for y. Now the question is, if the goal is to find y prime, would you want to find y prime with this, right? So yeah, it's kind of optional here, but I kind of wouldn't want to do it even if I could. So here, finding y is optional, but probably not recommended. Right, to find that, you're going to need to apply the quotient rule with all kinds of chain rules, and now I could tweak this very slightly and throw a product rule in there as well. Kind of not the thing you would want to spend your time doing. So let's not do that. And find y prime some other way, implicit differentiation. Right? So if I have 5x squared plus 2xy plus x fourth y squared equals 4x cubed, what I could do is just like last time, differentiate both sides. To differentiate this, product rule, right? So I'm going to differentiate the first thing, leave the second, plus, now leave the first, differentiate the second. Plus, this is another product rule, differentiate the first thing, differentiate the second. I get 2y prime because of the chain rule. This is just some inside function that I know what it is, but I'm not going to be writing it down. Okay, equals, plus product rule. Differentiate this, leave that alone, plus you leave this, differentiate that to y prime equals 12x squared. Right? So I apply the product rule here, differentiate the x to the fourth, leave the y squared, plus leave the x to the fourth, differentiate the y squared, applying the chain rule because the y is an inside function. On the right side, I would differentiate the 4x cubed, which by the power rule and the constant factor rule, we know it would be 12x squared. Now, our y prime is again just another member in this formula that I want to solve for, so it's a matter of algebra at this point, which we're all great at algebra by now. Y is a common term with these two guys. Because of that and that. And what I can do is take the other guys and move them to the other side. So this is going to be 12x squared minus 10x plus 2y minus 4x cubed y squared. And that's everyone. And now I can solve for the y prime by just division. Now, admittedly, this is a bit messy, but I assure you, it is a lot easier to actually do than to actually perform the quotient rule and the chain rule on that guy. And if you want to have some idea of how much of a mess doing it directly here would be, imagine this plugged in here, here, and here to imagine the length that your answer would be. Okay, it wouldn't be a fun time to do this directly. Yeah.
Do we order the term based on the degree of x or y?
No, we don't care the order.
Like,
Yeah, we just don't. We don't. Okay, so finding y is optional but not recommended in this case. Now you might still feel a little bit stubborn. You know what? I don't want to memorize a whole new method of differentiation, so I'm always going to just solve for y. And no matter what, I'll just brute force it, I'll take my chances. Let me introduce you to example number 3, which seems a lot easier to deal with or digest. Well, probably at first glance anyway. Now, it's probably not obvious to you at this point, so I'll just tell you. It is impossible to solve for y in this scenario. I don't mean it's hard. I literally mean it's impossible. Like, it cannot be done. You can prove mathematically that it cannot be done. This is an equation where if you wanted to solve for y, you couldn't do it. Okay? Now, something like that you'll prove in a class, if you're a math major. You'll eventually take a class called abstract algebra, in which you would prove things like that. So this is a polynomial of the 7th power in y. It can be proven that we only have formulas to solve polynomials up to degree 5. Beyond that, no formula exists. And beyond that, no formula can exist. No general formula anyway. For specific ones, you might get lucky and can solve them, but in general, polynomials of degree 6 or higher, you can't solve them in general. There's no solution that I could write down that would be y equals f of x, and f of x would make sense. So it's literally impossible to do it the first way here. But this might be an important relationship to me, and I want to be able to talk about rates of change in this relationship. In fact, it is an important thing. I forgot what it's called, Folium of Descartes or something. It looks like this. It is actually an important function to study, and that's what its graph is. It's not even a function really, as you can see. It doesn't pass the vertical line test. So actually solving for y, saying y equals blah, it's impossible. You can't do it. However, I can still find a derivative. I can still do calculus even though I can't solve for y. I can still find y prime by just saying, well, just differentiate both sides. Just going through differentiating everyone, I have that. Now my y prime is in these two locations, I can solve for it. Y prime is a common factor with this. I can bring the 2x to the other side. And so ultimately I can find my y prime to be minus 2x over 7y to the 6 over 2. That's the derivative. Now you might wonder, how useful is this expression? I don't even know what the y is, and you just told me it's impossible to even figure out what it is. Is this of use to us? The answer is yes. We'll talk about that a little more next time, and we'll do some more examples on implicit differentiation. By the way, our test is up to next week, Wednesday. It'll be everything up to this point. Yeah, no, I don't have the quizzes yet, but you should be able to